So one of the first things that we're going to begin with is we're going to talk about how we do these ions for our electron configurations. Right? Now, this is something that you should have done back in Chem 120, right? But in case you don't remember, when we talk about ion electron configurations or transition metals and going through their ions, remember that we're always going to lose our valence electrons first. So when you have something like nickel, nickel starts out with our looking like argon. Then we're on the 4s2. And then we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So when nickel becomes an ion, the two that it's going to lose are going to be from that 4s2. So they're going to lose their valence electrons first. And so we're going to become argon 3d8. Now I'm going to give you a moment. I want you to go through and do cadmium and zirconium as well. And let me see if I can clear up on my side what we're doing here. So I want you to go through and do your electron configurations for cadmium and zirconium. All right. Can you guys still see the worksheet on my screen?
Yeah.
Okay. So cadmium. So cadmium starts off with us losing 2 electrons from our valence ones. And so we should be losing them from our 5s2 first. And so we should be like a krypton, but we also have 10 electrons in our 3D, or not 3D, these should be 4D. And then with zirconium, we finally start to lose some of those d electrons as well. We lose our 2 from our valence, but we go down to only having 1 electron into our d electron, our d subshells as well. Does anyone have any questions on that part? So as you're going through these things, this is why our transition metals can start to have multiple valence states, right? Is that sometimes they lose just their valence electrons, sometimes they lose their valence electrons and some of their d electrons. And so as you're working your way through, you're trying to piece together what's been going on. So one of the ones to look at is something like our copper. Now the tricky part about our copper is copper starts off with an irregular electron configuration. Does anyone know what copper's electron configuration should be? 1 second. So as we're going through these electron configurations, what should it be for our copper?
Is it still going to be 40-10
argon and then 4010?
So when we first start off, it should be our argon, and we should have a 4s1
1 and then 5d
and then 3d10.
Yeah.
So what's irregular about our copper is that we start off without that s, or with only one valence electron instead of the two, right? So we've taken one from the 4s and we've moved into the 3d. And so that's why when we become an ion, our copper primarily forms just a +1 ion because we're getting rid of that one valence electron. So you do want to remember that you have your irregular ones. And if I pull up our periodic table, I can figure out how to do this. When you're looking at your irregular electron configurations, there's kind of 7 big ones that I would definitely recommend that you know. And then there's some additional ones on top of that. But when we look at our irregular electron configurations, manganese and technetium are a half shell. And so chromium and molybdenum, they both feature irregular electron configurations. They're going to have a 1 electron in their s, and then they're going to go to having 5 in the d shell, right? So those two are some that you want to remember. The other ones are copper, silver, and gold. All 3 of these go through an irregular electron configuration as well, because they go from having our 1 valence electron and completing the d shells, right? So you do want to know about those 5 as you're looking through your transition metals, because they start off at an unusual place. And that's the beginning part that you want to look at for those. So when we're filling the rest of these in, our scandium really just ends up looking like argon. Manganese ends up looking like argon, but it's got 1, 2, 3, 4, 5. Titanium is back to our argon. Vanadium as well, and also our osmium. So osmium starts 1, 2, 3, 4, 5, 6. And so osmium is going to be xenon with (5d5), and we also should have in there 4f14. And so that should be a review, hopefully, from CHEM120. If you're struggling with your electron configurations for ions, then we can always talk about that. The important part to remember is that your valence electrons go first, and then from there, you start to lose some of your d electrons. After that, you just have to remember that there are some irregular ones that you do want to be on the lookout for. The second part of what we're going to be looking at today is going to be us moving into the naming of the transition metal, or not the transition metals, of the metal or complexes. Now, one of the professors kind of compiled this list, and I thought that this list was very good. And so it's a kind of a flow chart in a way to help you work through naming the process, right? As you guys work through the coordination compounds. Some of them will be with salts. Other times they might not have the partner cation or anion, right? But you do want to know how to name them. And so you want to work through. And so your first step is just like when you name ionic complexes, always start with your cations. Right? We're going to start positive and then we're going to work negative. So if your coordination complex is the positive ion, then we'll start with your coordination complex. If their partnered ion is the cation, then we'll start with them. So for these 3, you can see that our ion was the cation. So that's why we're starting with potassium, lithium, and then potassium again. After that, after you've done your cation, then we're going to go into naming your ligands first. Now, ligands go through in alphabetical order. And it doesn't matter whether they're neutral or anions or cations. We're always going to go through and we'll name them alphabetically. This doesn't include the prefixes, so you don't have to worry about that part. And then the metal is going to be the last part that we name after all of the ligands. Now, these are your more common ligands, and so you do want to be familiar with these. For you guys' quiz in your exam, I will provide you with a list of ligands, and if it's not on your common ligands from table 23.3, I believe, then I would definitely give them to you. But you do want to know how to use them, right? So if I give you the ligands, if you're trying to still sort through and practice finding them and things like that, it will be a challenge in the same way that if I give you a periodic table and you have the names of all of the elements, it still takes you a while when you first start naming them because you have to find them, you have to remember their name, you have to remember their formulas, you have to work through all of that, right? So I would definitely recommend practicing them over time. You just end up naturally memorizing them, right? Like things like O2 minus becomes, it's your oxide or its ligand name is oxo, right? Bromo, chloral, fluoral, a lot of them are pretty straightforward. So it is something that you just want to make sure that you practice through. The other big one to remember is that there is this EDTA. Right? EDTA is a abbreviation of its longer name, with its ethylene diamine tetraacetate. And that's kind of like our large ligand that we will sometimes be using. It's a really common ligand, which is why it gets brought up so often. So in the same way that when you name covalent compounds, our prefixes are going to be mono, di, tri, tetra, penta, and hexa. In your slides, I do give you your bis, tris, and your tetrakis, which happens if you have like a ligand that already has one of these prefixes in it. And so you do want to know that that exists. As you go through, it won't show up as often. And so it is something that I would like you to know. It's a little bit extra, but it's not going to be the main focus of when we get into like testing on the ligands. It is still something that you should know. It might be there for the extra credit points. And so that's what I would recommend. The other part is there are some metals where when we give their names, we're not going to give them in their common names that we know them from. We're going to give them in their names that they're kind of like the elemental symbols are based off of. And so what you want to pay attention to with your metals is that if the complex is an anion, then we're going to end them all with 8. If not, we can just end them like usual. So if they're a cation, then we just use their name. If it's an anion, then we have to end it with an 8. So as we go through, these are the 6 that you do want to know have unusual names from their symbols. So copper becomes cuprum, which also becomes cuprate once we turn it into the anion. Right? Iron becomes ferrate. And so you do want to know those. You don't want to say iron 3 as you work through. So if we go back up and we look at some of these examples, you can see that they don't have this as potassium hexacyano iron 2. It's ferrate 2. Right? So you do want to know that part. And so then I've tried to give you a list of some practice ones so that way you can see kind of what it looks like. Now, something that's unusual with your metal coordination complexes, which we haven't seen in our ionic compounds, is you can have a metal that doesn't have an oxidation state. Something like tetracarbonyl nickel 0. And it's because that nickel is still acting like it's a Lewis. And so it's still interacting with your ligands, but because it's not really like a positive and negative charge, then we don't really want to assign them full oxidation states. And so that's how we can get a nickel 0, making that metal complex. So that's kind of like the intro to this. What I want us to do is we're going to actually work our way through for some of these. We're going to start off with their formulas and we're going to practice. Right? So, take a snip. So if we look at this first one here, this cobalt, this complex, is that going to be a cation complex or an anion complex? What do you guys think? So when we're looking at this one here, this complex, is that a cation or an anion?
Is it a cation?
It is going to be a cation, right? And we can tell this because we have to look at what it's partnered with. So it's partnered with chloride, and chloride is an anion. Right? So we have a positive metal complex, and we have our negative chloride. So we want to go through our ligands, and so let's break this down. We have NH3. Now, if we look on our list, NH3 is amine. And we have chlorine, which is our chloral. And so when we're trying to choose between those, which one should come in first when we go through our name? How do we choose which ligand to name first?
Alphabetical order, so amine would be first.
Alphabetical, so amine is going to go first, right? And so then we want to say how many of those amines. So we're really going through and we're naming our cation. So we're going ligand, ligand, metal, and then we're going to name our chloride. So we're just updating that first ligand. That first ligand is now going to become our amine. And there's 4 of them, so that's how we get tetraamine. The next part is we have 2 chlorals, so that becomes dichloral. And then we can name our metal. Now, do we need to do anything special to the metal when it's on the positive side? Or do we just list the metal as its normal name?
You have to add the O at the end, right? Chloral.
So we do that for the ligands. The ligands, when they're anionic, have the O at the end. But our metal by itself, so the cobalt side, we don't have to do anything with yet because it's the cation. So cobalt gets to stay the same. We only have to end it in 8 when it's the cations. Right? So we only have to change it to cobaltate if it was on the, sorry, not the cations, when it's on the anion side. So when our cobalt is on the negative ligand, then we change its name. So this only becomes cobaltate if our coordination complex was our negative one. Okay. So that's how we've got that first part. And so what does this 3 stand for?
The charge on the cobalt.
So it stands for the charge on the cobalt, right? So it's this oxidation state is really what we're talking about. And so when we do this, what you want to look at first is I always start with my counter ion. I start with my chlorine. So my chlorine, I have 1 of them, and I know chlorine is a -1 charge. So I know that that whole complex has to be an extra +1. And then we look at who it's partnered with. So it's partnered with chlorine and it's partnered with amines. Now, do amines have charge or are they neutral?
They're neutral.
Neutral. So our amines we're not going to worry about with regard to our charge, but our chlorides or our chloros, those definitely have a charge to them. So we have two chloros, and they're both a -1 as well, which is giving us a -3. And so that's how we can find out our cobalt needs to be a +3 in order to balance all of that out. And so that's what we're doing when we're working through on that part. So let's look at this platinum one. I want you to go through and without looking at your answer key over on the right-hand side, go through and name it on your own. What does our platinum one look like? And then we'll walk through and we'll piece that together as well. So try to name your platinum one on your own first. And so if you have the first page of your worksheet, right, you can actually hold on to it all by itself. It's got your answer or your steps on it, and you want to work your way through from that part on. So for this part, our ligand is also going to be positive again. And it's partnered with our negative nitrate. Now using our list of our ligands, we should be able to know what this En is and our Cl, right? So we have chloro once again. And so what does En stand for?
Ethylene diamine.
Ethylene diamine. So which of these is going to go first? Is it going to be our chloro or is it going to be our ethylene diamine?
Chloro.
Chloro. So how many chloros are there?
Two.
Two. So we should start that off with dichloro. And then how many ethylene diamines do we have?
Two.
Two. So normally what will we use for our prefix if we had two?
Di.
Di. But because we already have a diamine inside of that ethylene, this is why they have us use bis. So bis is there to tell everyone that you have two ethylene diamines. If you had used diethylene diamine, you would think that you had four different ligands there. You would have two ethylenes and two diamines. So that's why they use bis with those parentheses, is it's letting them know that there's two of the ethylene diamine, which is one ligand altogether. So we have that part all set up. Do we need to change anything about our platinum? Do we need to change its ending or can we leave it as platinum?
Leave it as platinum.
Leave it as platinum. And so we do need to come up with its charge for the platinum. So for our platinum, we're looking at our oxidation states. We have two chloros, each one is a -1. We have two nitrates, each one is a -1 as well. And we have one platinum trying to balance out all of that -4 charge. And so our platinum should be what oxidation state?
+4.
+4. Very good. We'll do one more example up here where you guys have an answer, and then we're going to skip down to the next section where we'll do them on our own. And so let's jump to a different one. Let's look at this one at the very bottom, the K2COCl4. Let's look at this one right here. So for our K2COCl4, which one are we going to start off with for our name?
Potassium.
Potassium, right? Always with the cations. So we start with our potassium first, and then we're going to go into our metal coordination complex this time. Now, do we need to do anything about alphabetical order for our ligands, or do we only have one option?
Just one option.
Just one option. So tetrachloral is definitely going to come next. We don't have to worry about alphabetizing them. And so now that we've done our ligand, what do we need to name next?
The metal.
The metal. Now, do we need to do anything to that metal because it is now an anion?
Yeah, this is when we had the 8.
This is where we add the 8, right? And so that's what's making this apart. So it's not necessarily that the metal itself is the anion. The metal still has a positive charge. It's just that altogether, that whole coordination complex is going to be an anion. It's going to be a negative charge. So now we need to figure out what that oxidation state should be for our cobalt. So we partnered this up with 2 potassiums. So that's our +1. We have 4 chloros. Each one is a -1. And so our potassium, oh, sorry, not our potassium, our cobalt needs to have what oxidation state in order to make that balanced? If we're getting 2 positives from the potassium and 4 minuses from the chlorine ones, which one do we need to take care of first? Oh, sorry, which oxidation state does our cobalt need to have?
2.
2. Very good. So as you work through, remember that you're always going to name the cation first. So that could be either the metal by itself, so in this case, the potassium, or it could be our coordination complex. It all depends on what charge they have. Now, an easy way to know is that when you look at your complexes, generally speaking, if you're writing your formula correctly, the cations are going to be listed first. In the same way that when you do ionic formulas, you don't write FLi, everyone writes it as LiF, right? You're always supposed to put your metal or your cations first. And so when you look at your coordination complexes, that's one way to tell. So let's jump to the questions. We're going to look at part 2, and we're going to start going through these. So you can go ahead and get started with your part 2. So we'll start with that first one, that ruthenium one. Now, when we look at this one, is this all one ligand or is this a salt? Or sorry, not ligand, or complex. What do you guys think for this one? Is it a salt or is it just the metal coordination complex? So this is just going to be the complex. And you can tell because we have these charges left over. If it was a salt, we wouldn't have those charges. So we're not going to have an anion or a cation partnered with our complex. We're just going to have the complex. So all of this is part of that complex. So when we look through these, we should list our two ligands. We have amines and we have chloral. So we should start with our amine. So we have pentaamine. Chloral. Ruthenium. And then what should our charge be for our ruthenium?
Three plus, 3 minus.
It should be
3 plus.
3 towards oxidation state, so plus 3. Yep. And so that's what we're looking for that one, right? It's pentaamine chloral ruthenium 3. Looking at our next one, we can go ahead and start to piece those together as well. Now, this might be something you haven't seen before. Right? What do you think the name of that one is?
You asked what the charge is?
What is the name of this middle section here? This part of this NH2, CH2, CH2, NH2.
Does it have something to do with ethane?
It's going to be with ethylene, right? And so this one is diethylene diamine. Or sorry, it's ethylene diamine. So this is our EN. That's the formula for EN. That's what it actually looks like, right? Which is not as commonly written all the way out, but it's important that we do recognize it when it is, right? And so if you ever start to get into these really long ligands and you're not quite sure what it could be, right? It's generally going to be your ethylene diamine, or if it's insanely long, then it could be your EDTA, right? Because not only would it have this, but it would have 4 acetates as well. Right? So this stands for our EN. So do we just put triethylene diamine, or do we need to do something special because it's ethylene diamine?
Tris.
Right? So we need to use tris. So this should be tris, parentheses, ethylene diamine. And then we have manganese.
Why is NH2 amine still, even though it's not NH3?
So
Why does that 2 not make a difference?
So NH2 is considered an amine because it has the same functional group. It's just that it has to trade off one of its hydrogens to be attached to the CH2. Right? So it still ends up being the same type of ligand per se, in that it's doing the same chemistry. It just has to give away one of those hydrogens in order to attach in.
Gotcha.
So this is our manganese, and then we have, does ethylene diamine, is it neutral or is it an anion or a cation for its ligand?
It's neutral.
It's neutral. And so this should be an oxidation state of 2. We can do our next one as well. So this is going to be something different about this. This has a negative charge as opposed to a positive one. And so while we start off the same, we start off with this hexacyano. What do we need to do for that iron?
Add 8. Make
We have
it
to add 8 to it, right? Because it is their anion, it should be ferrate. And what oxidation state should our ferrate be?
2.
2. And we know this because it's got a -4 charge, and each of those cyanos is a -1. So if our ferrate is a +2, then that's how we'll get that -4 charge overall. So when you're going through and you're looking to name these compounds, you want to be using your ligand sheet for this first part until you start to feel familiar with it, right? I've separated them through your anionics and your neutral ones. One way to tell for your anionics versus your neutrals is if you ever get their names, if they end with an O, it generally means that they're an anionic, right? Because everything from bromo, right, chloral, fluoral, what they've done is because they're in ligand, but they're an anion, they've changed the ending from the "ide" to the O, or the "ite" or "ate" to "idol" and "atol." The neutral ones normally just keep their names as a whole molecule. So that's how you get aqua, carbonyl, amine, right? They don't end in those O's. That doesn't help you when you start off with the formulas. You do have to know that second part. And so right now, start with your list and work your way through about anions versus your neutrals. And as you do more of them, they'll become more familiar about how you classify them. But there's not really a perfect way to know. You pretty much have to memorize them, similar to what you had to do with polyatomic ions. We're going to do one last one, so that we'll do this cobalt one down here. And then we're going to move on to the second section, which is very similar to this. So go ahead, write in your name. And then when you guys are done, I'm going to create a poll because I would like to see what your guys' answers are.
Wait, which cobalt one? There's a couple different ones.
Sorry, we're going to do the next one on the list, so the fourth one down.
Okay, thank you.
Once you guys have your answer, go ahead and put it up in chat, and let's see how we did. Once you guys have it, you can put it up in the chat. I'm curious to see how you guys are doing with this. Let me see how we compare. So we have the first answers kind of coming in. And so a couple of things to check, right, is think about how you come up with your ordering of your ligands, right? Which one should come first, which one should come second. The other one is we should be thinking about how should our metal end? Is it just going to be cobalt or is it going to be something else? So I've worked my way through to do our name, right? Now, when we have two choices, we have the amine versus the nitrile. We should be putting them in through as we alphabetize them. So we should indicate which ones come first. Then we should name them, we should name how many after we've listed them in order. So we should have our pentaamine should come first before our nitrile, because amine starts with an A versus nitrile, which starts with an N. Once we have the amine coming first, now we add in the penta in front. And so that's how we get pentaamine nitrile. Right? So compare your ligand names, not the names of the ligand with the prefix. So just the ligands. So it should be pentaamine nitrile, and then we should have that metal cobalt with our 3. Now, because it's not an anion, right, this one is still a positive charge, then we're leaving it as just cobalt. But otherwise, you guys did very well on that part. So just remember, as you're listing them, alphabetize your ligands first and then worry about how many of them you have. Any questions on that part? So like all naming things, I recommend practice, right? So you want to keep going through, you want to eventually get all of these written out. It's important to practice that part. But we're also going to look at our next section now. Our next section is very similar. The difference is that these are now salts. And so I want you to go ahead and start with this potassium one right here, the second one down. We're going to do that one next. So we're going to go through and name our potassium one. There we go. So this is the one that we're going to be looking at here. Once you go ahead and get your name, you can put it up in the chat as well, and we can go through that. It stays very similar to what we just did. The only difference is we have this K4, and so we have to account for that. How does that change things for us? So remember to name your cation first. We don't have to worry about the alphabetizing our ligands. If you make a mistake, go ahead and rewrite your whole name, just so we can know exactly what you wanted to swap out there. So once you guys get your answer, go ahead and put it up in the chat and let's see how we're comparing. Interesting enough, we actually haven't had a correct answer yet. There we go. So as you're going through this, right, we wanted to start off with our positive part. So we should have our potassium. I should share this with you guys. So we should have our potassium going first. Right? From there, we do have our ligands. So we're doing hexachloral, right? And so that part we all seem to be in agreement about. The second part that we need to change is we have to account for the fact that our platinum is in a negative ion or a negative complex. So it's in an anionic complex. So we shouldn't have just platinum. We should have an ending there. It can be either platinate, or I would have also accepted platinumate. Both of those would have been fine, right? And our oxidation state in this case should be a +2. So we have 4 potassiums plus our platinum should be equal to our 6 chlorines -1. So this is +4 plus platinum equals -6. So our platinum should be a +2. So as you guys are comparing those, right, just keep that part in mind. So we should have them all with our 2 for our oxidation states. And then this other part is make sure that if this is a negative complex, that we're changing those endings. We have to add in that 8. Let's try it.
Is the one that ends in platinate or platinumate?
I would take both. It's really platinate.
Yeah.
But that part would be fine as long as it ends in that 8 is what I'm looking for, right? But they should be the platinate. We're going to try another one. We're going to look at this one down here, this cobalt amine one. And so once again, we'll do that same thing. Let's see how we did, and then we'll compare.
Is this still a salt?
So
So is it a complex ion now?
it's not a complex ion because it doesn't have a charge.
Right,
It
right.
is a neutral complex.
Okay.
Mhm.
Do these end in 8?
So our ones that end in 8 should only be when it's an anion. So if it's neutral or if it's a cation, then leave it with the normal ending.
All right. Just it. So only when the complex ion has a negative charge to it is when you have it at 8.
That is when we have the 8.
Okay.
Very good. So when we're looking at this one, we should have our amines coming first and then our nitro. And both of them are 3. So it should be triamine, trinitro. And then we have our cobalt, and we don't need to change the ending of it. And so our cobalt needs to be a 3 for its oxidation state in order to balance out the -3 from the nitros. So very good. Now, one part to remember is that with your amine is when it's the neutral ligand, it has 2 M's in it, right? So it's AMMINE. When it gets introduced as part of that the ethylene diamine, right, in the EN, or also in the EDTA as the diamine, it goes down to just 1 M. I don't know why that is, just is the way it is, right? So just be aware about that part. The next one that we're going to look at is we're going to look at this one right below. We're going to look at the chromium one. And so be very careful about how you end things, because we have bromine that's associated with the complex coordinate, or the coordination complex, and we have bromine ions that are balancing out your salt. So think about how that changes things for your name. So as you're answering this, think about when you name ions, right? What's the difference between bromate versus bromide?
Right, because this is a neutral. There's no charge on the Br, so it's not going to be bromate. It's going to be bromide.
So they all have charges on them, right? But is
the whole thing?
Well, so the part that's coming after the chromium, which bromine are you referring to?
The one on the right.
Right.
One
So
outside.
if we're looking at this bromine over here, is that bromine part of your metal coordination complex?
No.
No, right? So this Br2 is really looking for this ion, right? A bromine with a -1 ion. So anything that's not in the complex, we don't have to worry. We name it like we normally would. Right? So it's almost like we have a positive cation here, and we have negative anions here. So once we go through the naming of that metal complex, so that's the penta, aqua, bromo, chromium 2, or chromium 3, we're going to name that ion separately. And so we use the "ide" because it's just the element. If it was bromate, right, then we would have that with our oxygens involved. And I think it's like O3, right, in order to balance those out. So once you're not part of that complex anymore, you want to follow your normal or your traditional naming rules. So we only end in these 8s, like for our platinate, we only add that in when it's part of our metal complexes. Even though it's next to the metal complex, doesn't change how we would name this Br part. And so that's how we end up with just bromide. Does anyone have any questions on that part? So we'll do one last one in this section. Let's look at this platinum one all the way down here at the bottom. So this is different because we have 2 metal coordination complexes coming together. We have one as our anion and we have one as our cation. So think about how might that change things for us as we start to name them.
What's the charge on platinum iodide?
So
how do we know what the charge on there would be?
what you want to think about is think about your platinum, what their oxidation states might look like, but also if you start with your platinum I4, can kind of give you an idea about where things might need to go. So we're going from a 4 and we have a 2 on one side, right? So we have platinum with 4 eyes and we also have platinum with 2 eyes.
But for them to be neutral, don't they have to equal the same charge?
So one's got to be positive and one's got to be.
That's
so
what I'm saying.
yes.
So wouldn't the charge? But how would the charges be? Well, the platinum is going to change charges, I'm guessing.
Your platinum is going to change charges.
Okay. Fucked up.
Very good, you guys. So this one was a tricky one, right? And so part of this is knowing that platinum normally exists as a +4 or a +2 or a +1, right? And so as we're working our way through, we named our first one tetraamine diiodo, right? Because we have the amines coming first, then we have the iodo. And we had a platinum there. And so you might not have known what your charge is. So that's fine. We'll come back to our charge in a second. We'll do how we'll show you how you get that part. On the second part, we have tetraiodo, and then we should have a platinate there because it should be in our anion. So we should have some negative charge here in our second one, and we should have some positive charge here. Now that change has to be related to our change in our iodines, which is a -2 overall. So this one on the right should be -2 down. This one over here should be a +2. And that's kind of how we find out which one should be the 4 and which one should be the 2. This first one ends up being the 4, so that way it gets a +2 charge overall. The other one ends up being a 2 to be a -2 overall. You could have also had it with platinum being 2 and our tetraiodo platinate being 4, except then you wouldn't really have an anion and a cation coming together. You would just have two neutral complexes. And so it wouldn't have been written like this, because this kind of implies that there should be a negative charge on one side, a positive charge on the other. Right? And so that's the difference there. We should be using the tetra and not the tetrakis, or we should be using the di instead of the bis, because these don't have any prefixes with them, right? Just because that the di and the iodo are similar to each other, we only use the bis if there's already a diamine inside that compound. So when we used it with our ethylene diamine, inside the name of that ligand, there's the di, right? Or if it was like ethylene triamine, there's a tri in there, and that's when we have to use bis, tris, and tetrakis. So we only use it when the ligand's name itself already has one of the Greek prefixes inside of it. And so we see that with like our EDTA, we see that with our EN. Right? Those are our two most common ones where we see that. And so that's the naming part. The naming part, you want to practice going this direction. On Thursday or on Wednesday, we'll also practice going the opposite. So I'll give you guys some of these names for the complex coordinate names, and you guys will have to come up with the formulas for them as well. Right? So you do want to practice going back and forth as you work your way through these. It's sometimes harder than we think to go backwards on them. Does anyone have any questions on naming before we move over into this orbital splitting? So I'll tell you the same thing I tell my CHEM120 people, right? Naming is about repetition and it's about being systematic as you work your way through. So I would strongly recommend that you practice, practice, practice. And it is one of those skills that really benefits from doing more of them. Right? And so if we were just doing nomenclature, I would say do 100 of them before your quiz, right? Since we're only doing the metal complexes, it's not quite as many, but I would say that you should probably be doing more than 10, probably less than 50, but somewhere in there, you want to make sure that you're practicing those. Okay. We're going to look at this next section now. We're going to look at our d orbital splitting, and I've already told you for these are all going to be octahedrals. Okay? So I've given you kind of like their splitting diagrams down here at the bottom. And so we're going to compare them with our low spin versus our high spin. So the first thing that we have to do with this is we have to figure out how many valent, or not valence, how many electrons do we need to account for? And so we're looking for our number of electrons in the d orbital. So go ahead and look at iron 2+ and cobalt 2+ and figure out how many electrons they should have in their d orbital. The quiz is on Wednesday. So in Wednesday's quiz, we will be covering chapter 20 and chapter 23. Most of it will be focused on the naming side for chapter 23, and then some of the applications from 20. It won't be quite as long as our last quiz. So it'd probably be closer to 45 minutes instead of an hour. So for our iron, when we've given away our 2 valence electrons, we should have a total of 6 in our D. So this is going to be D6. And our cobalt is the next one over. And so it has D7. So we have to deal with 6 electrons and 7 electrons. So when you think about high spin versus low spin, a lot of what it's talking about is it's talking about your magnetism, with high spin being unpaired electrons, low spin being paired electrons. So the more unpaired electrons you have, the more spin you get, because it's really talking about your MS. So when you partner electrons up, when you have one going up and one going down, your spins are canceled. You don't see any magnetic spin because you're one spinning positive, one spinning negative. So when we're talking about high spin, we're really talking about having a lot of unpaired electrons. So this happens when we attach ligands to our orbitals, and this is the crystal field splitting. When ligands are associated with our metal, the d orbitals no longer are degenerate. They don't all have the same energy. Some of them start to interact with those ligands more, and so they become a higher energy. Some of them become a lower energy because they don't overlap with those ligands as much. And so that electron-electron repulsion gets adjusted for them. So we have high spin and low spin when we start to attach ligands to these metals. The larger the gap, the lower spin is going to be preferred. The idea is that the benefit that we get from spreading out our electrons is not enough to overcome the difference in the energies between the top orbitals versus the bottom orbitals, right? So our high energy orbitals versus our low energy. When we're in high spin, then they get kind of spread out evenly throughout them. So when we look at our iron for our high spin, it means that we have 6 electrons to put in. So we put in our first 3. For our 4th electron, we have a choice. We can put it down here in the bottom, or we can put it up in the higher energy orbitals. For our high spin setup, we're going to put it up on top, 4 and 5. Because this delta E, the difference in their energy is small. So those electrons would rather make that step up into the higher spins or the higher energy state for them to get their own orbital. And our last one should be down here. For the low spin's not able to kind of make that jump. So our first 3 look the same, 1, 2, 3. But number 4, instead of going up on top inside of its own orbital, goes down here at the bottom. Same with 5, same with 6.
So this can be both high and low spin?
So iron can be high spin or it can be low spin. Because it's not about the metal, it is about the ligand that it's partnered with.
Right.
Yeah. So right now we're just drawing both the high spin state and the low spin state for each of them. So that way we can really clarify what the difference looks like between a high spin and low spin.
Oh, so if it was like connected to cyanide, you'd still only have 6 to use, but you'd have to put them in whatever cyanide was a high spin or low spin.
So if we were looking for a specific one, let's say like if FNCN, right? Then we would be looking at just one of those options, right? So we would have to look at CN, we decide if it was strong field or weak field, and then we would choose it to be the high spin state or the low spin state, depending on that.
Gotcha.
Right? So we would have to be looking at the ligand on that part. For right now, I just want to have us practice drawing what the high spin looks like, what the low spin looks like, because I feel like the other part where you just look at the ligand is not the tricky part of it. So go ahead and draw out your cobalt. And what does its high spin state look like versus its low spin state? So with D7, our high spin state should be 1, 2, 3, 4, 5, 6, 7. And so we should have 3 unpaired electrons. For its low spin state, we should have 1, 2, 3, 4, 5, 6, 7. We should have 1 unpaired electron. Does anyone have any questions about our orbital diagrams? Then I have a new question for you guys. How many electrons are there in the D subshell?
10.
10. So there's 10 electrons. And so with our high spin and our low spin states, we're really only focused on the D subshell because we're just looking at that transition metal in the beginning, and they've given away all their valence ones. So we're really only concerned with those 10. Now, we could have a metal with 1, 2, 3, 4, all the way up to 10 of them. And so what I want to ask is there a difference between their high spin and their low spin state for each of these. Right? So you just need to answer yes or no. So as an example, if I look at my D1, I have one electron in there. Doesn't matter whether it's in the high spin or low spin state. There we go. Can you guys see this, the whiteboard? Okay.
Yes.
Doesn't matter whether it has the high spin or low spin state if we're in the D1.
No.
No. Okay. So we can go ahead and we can answer this one as being no. So I want you to go through for each of those 10 valence electrons, or not valence electrons, d electrons. I want you to decide whether or not it can have a high spin state or a low spin state. So which one of those matter and which one of them don't. Because if we think about it, if we go into D2, those look the same. This says there's no difference between them. So when we get to the end, we should be able to list which D1s have a difference between their high spin and their low spin. And so when you find your answer, go ahead and put that in chat. Which one of these have a difference between the high spin and the low spin?
Like the first one that does?
The first one all the way to the last one that does.
Hmm.
Excuse me. I realized I drew too many boxes up here. So when we look at these, right, as we look at our different options, there's actually a very small window where our high spin and our low spin matter. Once we get to a lot of electrons, then we've already filled the bottom level. And so we're going to look the same in our top. When we don't have enough electrons, then it doesn't matter as well. So the range where high spin and low spin matters is between D4, D5, D6, and D7. More than that, and our orbitals look the same. Less than that, and our orbitals look the same as well. Does anyone have any questions on that part? Are you guys ready to move on, or do you want to do more with the spins?
I feel comfortable with the spins right now.
Good.
Everyone else.
So what we really want to do with the spins is be able to like kind of apply it a little bit. So when we're looking at magnetism, things like that. And so question 5 is having you guys apply it. So when you look at those, think about when you have high spin or low spin, whether or not that's making more electrons that are unpaired or less electrons that are unpaired. So let's change this screen up. So when we look at number 5 here, right, it's saying that with our cyano-CN, that we end up with 1 unpaired electron. With thiocyanate, we end up with 5 unpaired electrons. So which one should be our low spin state? Is that going to be our iron with the CN, or is it going to be our iron with the SCN? So our low spin state is going to be with the CN. Our high spin state is going to be the SCN, and it's all about your unpaired electrons. So if we look at it, right, we're trying to compare 1 unpaired electron versus 5 unpaired electrons. So our iron is going to be a +3, which makes it a D6. Sorry, not a D6. It should be a D5. There we go. Let me try to clean this up a little bit. Versus the other D5 looks like this. So we have 5 unpaired electrons versus our 1. So this is our high spin. This is our low spin. So if we have high spin, is that going to be a small splitting or a big splitting? If we have high spin, is that going to be a small gap or a big gap between our 2 energy levels in our d orbital? What do you guys think? So if we can evenly spread out between them, this means that there's going to be a low gap. Because it means that the jump between the 2 levels isn't enough, it's almost like they can be spread out throughout the same. When we go into a low spin state, this means that there is a big change between them. We would rather partner up than go to the higher energy orbitals. So just like Hund's rule, where we kind of want to put one electron in each of the orbitals by itself, the more of Hund's rule that we follow, then the closer those energy levels are. So right now, this is a high spin state, means that there's small change. And if there's small change, then that means that we are a weak field ligand. If there's a high change, what kind of ligand do we need to be?
Strong.
Strong, very good. And so when they're looking for an explanation, we could say that SCN is a weaker field ligand than CN because it doesn't split the energy levels of our d orbitals as strongly, which is why it can be in a high spin state compared to the low spin state of the CN. You can also draw out your diagrams, one for your CN, one for your SCN, and then showcase how the low spin means that the gap needs to be smaller, and then that means that it has to be a weak field compared to the other one where we have the pairing, and so that's going to give us our low spin state, which means there's a big gap, which also means it's strong field. Any questions on that part? Okay. We're going to go down to number 6 right now. So we're going to look at this question right down here. And so when you're looking at this, right, there's an important part to remember about absorption versus what we see. Right? And so your eye doesn't necessarily see the lack of light. Always, what we normally see is we're seeing what's being reflected, or we're seeing what's being transmitted through it. So when we talk about that, it absorbs yellow light. It wants us to know what color does it appear to be. Now, I'll provide you with the wavelength cutoff field values so you guys can see that as well. But a simple way for you to do these comparisons is go ahead and draw a circle and split it in half. So we're going to make this pizza pie with kind of 6 different slices. And this is going to take our visible light range, and we're going to get the complementary colors that we see from that visible light. And so as you walk through it, the shorthand name is Roy G. Biv. We actually don't have any I though, so it's just going to be Roy G. BV. And so that means that if this is red, our next one is orange, and our third slice is yellow. This becomes green. This is blue. And this one is violet. So Roy G. Biv kind of gives you the energies of the different colors. It also gives you the colors of the rainbow kind of in order. So this is our long wavelength. This is our short one. If you ever need one because it has a specific cutoff value, then I'll be providing the chart. But right now, when things absorb, what we see is the kind of like complementary piece. So we go across the chart to the other one, and that's what we're going to see. So if we have all of these colors, we would see white. As you start to absorb one, your eye picks up the extra purple that gets let through, and that's why our solution will appear that color. So in this case, as we absorb in that yellow light, let's see if we can do this. Let's say that this is our vial there. That's our solution. As the light all comes in, the yellow gets absorbed here. And so what we see on this side is going to be what color?
Violet.
The violet. So the same amount of violet gets through, but because it doesn't have the complementary piece, that yellow, to kind of cancel it out inside of your receptors, then we see that purple color, that extra purple come through. And so that's why we see that solution as being purple. So it's not that it absorbs purple and so we see it as purple. It actually absorbs the opposite side. So it absorbs yellow and so we see yellow. Oh, sorry. It absorbs yellow so we see purple. If this was emitting photons, then we would see that. So if it emitted yellow light, we would see it as yellow. But if it absorbs yellow light, then we see it as purple. Does anyone have any questions on that part? So just as a quick one, if we wanted a solution that was a blue color, what do we need our wavelength of light, or what wavelength of light do I want it to be absorbed at? So if we want blue, or looking at our chart, right, we want it to absorb an orange. And so what wavelength does our orange need to be?
580 to 650.
580 to 650, right? And so then later on, you guys would solve this for your energy of that. Does anyone have any questions on that part? So the last part that we're going to do is we're going to work on these isomers a little bit. We're going to actually continue with the isomers on Wednesday as well. So we'll do some more of this practice with isomers on Wednesday. I'll be adding on to this worksheet with some isomer focus for Wednesday. Right? And so we're going to look at one of these. Let's go ahead and look at B. I think B is going to be a little bit cleaner as we start to do that comparison. So let me copy this. So when we're looking at this cobalt, right, we would like to know our coordination number for our cobalt. How many things is it associated with? So for cobalt, right, what we want to look at for coordination number is we look at your number of ligands. We do want to adjust for if any of them can bind more than once. So there's a couple of ligands that bind more than once. And so we do have a chart for those on 23.3. So for these ligands, how many times do each of them bond? So like for our nitro, how many bonds can it make? What do you guys think for our nitro ligand? How many bonds?
It has 3, right?
For our nitro?
Wasn't there a total of 6? Like the
So we're just looking, so for our nitro here, we're just looking at one of these NO2s. How many times do we need to account it for?
3.
Right? So our NO2, each one makes one connection to that cobalt, and then there's 3 of them.
Yeah, 3. Oh,
Yeah. Now for our amine, how many does that one make?
3 as well.
Right? Because there's one of them and there's 3, or sorry, each one makes one bond and there's 3 of them. So our coordination number is going to become 6 because we have 6 ligands attached to it. this coordination number is how we figure out our basic geometry of our complex. So if you have a coordination number of 6, what's your base geometry that you need to start from?
Octahedral.
Octahedral. Right. And so in the middle, we would have our cobalt. And then around, we would have our NO2s and our NH3s. So go ahead and spread out your NO2s and your NH3s. I want you to think of how many unique arrangements you can come up with for your NO2s and your NH3s. Now, one way to do this is you can just assign them colors. Right, so that might be my NO2. And that might be my NH3. And that might make it a little bit easier for me to keep track of them as I start to draw them out. If you have a modeling kit, you can also do it that way as well. Now, how many different isomers were you guys able to come up with?
Shouldn't there be 3?
And so what are your 3? How do you find that?
Well, I have, yeah, like the first one you drew where they're both on each side. And then like, yeah, the second one. And then wouldn't the third one be where it's every other one?
So if we do every other, oh,
Or would every other one be the same as the first one?
well, let's see. So if we do every other one, so you're saying that this one, and then.
Yeah, it's hard to see when it's like flat. You know?
Yeah. So if you do.
That would be purple there.
Yep. But that's the same as our second one,
Mm-hmm.
right? If we rotate this around, right? If our purple went back up on top. So we've rotated it over. This is going to be the bottom, right? And then if we turn it to the side, so like this one's coming this way. This becomes blue. This, oh. This one becomes blue. And then these both go back to purple.
Same one.
It ends up being the same one. So how many different isomers do we have?
2.
Just 2 on this one. And so for most of our octahedral, there's really only 2 options. It's either going to be they're all 90 degrees apart, or somewhere in there, there's going to be one that's 180 degrees apart. So this would normally be called our cis isomer, and this one would be our trans. Because this trans has one that's 180 degrees, so this purple to this purple, right? That's 180 degrees. Whereas all of these other ones are cis because only 90 degrees away from each other. Does anyone have any questions on that part? Isomers are tricky, right? We'll spend more time with them on Wednesday. And so when you get to this part, I just want you to practice drawing some of them out. I'll put up an answer key for this, and then we'll go over them more in depth again on Wednesday. Right? Knowing cis versus trans isomers will be on your quiz, but you won't have to draw any of them. So what I would say is if you can identify them as cis or trans, then that's going to be enough. Optical won't be until your exam number 3, right? So you won't have optical isomers on your guys' quiz, but it is something that you do need to know for exam number 3. Right? And so we talk about optical ones on Wednesday as well. Okay? So work your way through these. And then you're basically just trying to draw out however many isomers as you can see. Does anyone have any questions on that? You can use kind of like what I've done on mine. You can use symbols to stand for your different connections. What I would say though is you should practice knowing at least which one of these options should be connecting, right? So if we have this as our CO, our carbonyl, we should know that that carbon is connecting for that carbonyl as compared to that oxygen. So just think about that as you guys are drawing them out. But I want you to make an attempt on your isomers. We will work on that together on Wednesday as well. Did you guys have any other questions on things before we kind of wrap up for today?